Okay, so in this video we're going to continue to talk about radioactive decay and introduce the concept of half-life. Okay, please make sure that you're taking good notes as we go through this video. If you look at this slide, it says, recall that the approximate definition of radioactive decay is this: a random, spontaneous process in which an unstable nucleus disintegrates, in the process emitting either an alpha, beta, or gamma particle. Now, we've talked before about, what that means by unstable. That means there's an imbalance between the strong nuclear force and the electric force, the Coulomb force within, any given nucleus. Disintegrates just means breaks up into pieces, and we've seen that before, how an unstable nucleus can, emit some type of radiation and turn into a daughter nucleus. Okay, that's called transmutation when one element turns into another element. Now, what does random and spontaneous mean? Okay, what do you think is meant by random and spontaneous? Well, random in this case basically refers to the fact that if you have, let's say, a bajillion atoms, there's no way that you can predict which atom is going to decay next. Even if they're all radioactive, there's no way to predict which one is going to be the next one to undergo radioactive decay. Spontaneous just means that it can happen at any given moment. Okay, and there's no way to predict when or which unstable atom is going to decay. However, if you have a large collection of radioactive atoms, then we can apply some statistics to the situation to get a better understanding of how the situation is going to unfold. Okay. And so on this slide, again, make sure you're taking good notes as we go through there. Pause it here if you need to add this to your notes. Okay, so the first bullet point says radioactive decay is random in the sense that there's no way to absolutely predict whether or not a given nucleus will undergo decay. The best we can do is talk about the probability of decay. However, if we start with a sample of radioactive material, for example, uranium-238 undergoing alpha decay into thorium-234, and we measure the rate at which the nuclei decay, we discover something very interesting, which is known as the law of radioactive decay. Again, this is something that should be in bold because it's a vocabulary term, so I'm going to put that in bold, and I will read to you what the law of radioactive decay says. Okay, here's what it says. It says the number of nuclei that will decay per second is proportional to the number of atoms present that have not yet decayed. Okay, let me read that one more time. The number of nuclei that will decay per second, that is the rate of decay, how quickly the decay is happening, is proportional to the number of atoms present that have not yet decayed. Now, what that means basically is if you have a sample of something that's radioactive, the more atoms that have not yet decayed, the faster the decay is going to happen. In other words, how quickly those atoms decay into something else depends on how many yet have not yet decayed. So in other words, if we have a rock that's 100% uranium-238, at the beginning when it's all uranium-238, it's going to be decaying very quickly. Okay, as uranium-238 begins to turn into thorium-234 from alpha decay, we end up with less uranium, and because we have less uranium remaining, the rate of decay is also going to decrease, because the rate of decay, it says, is proportional to the number of atoms present that have not yet decayed. So in other words, our radioactive piece of uranium is going to decay more slowly over time as there's less and less and less uranium remaining. Okay, just one more vocabulary term. The rate of decay, how many decays we have per second, is known as the activity. I don't know why it has that name, but activity refers to the rate of decay. Okay, so the unit for activity is called the becquerel. We use a BQ for that abbreviation. It's named after some physicist who investigated radioactivity, Becquerel. He was French, I believe, where 1 becquerel means 1 nucleus is decaying per second. Now, what does this mean, that the number of nuclei that will decay per second is proportional to the number of atoms present that have not yet decayed? Well, if you ever go farther in science or math, this type of behavior is very interesting to investigate. It's going to produce something known as exponential decay. And I don't want to get too mathy, but that type of relationship is always going to produce exponential decay, which looks something like this. Okay, the more unstable nuclei you have, the faster they decay. If you take a look at this graph here on the right, you can see the rate of decay is represented by the slope of this graph. Now, as the graph goes on, we can see that the slope starts off very, very steep and negative, and the slope slowly decreases over time until it's almost completely horizontal at the end. Okay, so that's characteristic of exponential decay. So, what I'm saying is anytime you have something that's radioactive, the amount remaining decreases with exponential decay. Alright, now both the number of radioactive nuclei in the sample and the activity of the sample decay with the same half-life. And so the next question would be, what does that mean by half-life? So I'm not talking about the video game. This is another definition thing that we'll see on the next slide. Okay, but make sure you add this to your notes. In other words, so this is a graph of how many counts we have per minute. So this is basically showing a rate of decay graph. If we had a graph showing the number of nuclei remaining as a function of time, it would also look like exponential decay. But let's talk more about this half-life thing. Okay, so this is another vocabulary term that you need to know. On this slide, here's the definition of half-life. Okay, half-life is the time it takes for half of the amount of unstable nuclei in a sample to decay. Please do not forget that definitions are important, and I say that just because, you could always have a question that asks you for the definition of something. Also notice that half-life is by definition a time. Now, the typical way to write half-life is to use a capital T for time and then to put a subscript 1/2. Okay, so T1/2 represents half-life. Now, for any given radioactive substance, this is usually a constant value. Okay, so here's a simple example. Let's say I start with 100 grams of an unknown radioactive substance, which has a half-life of 10 minutes. If it has a half-life of 10 minutes, the half-life is not going to change, even though the amount might change. Okay, so half-life is a fixed quantity for a given radioactive material. So I would write T1/2 equals 10 minutes. And what that means is it is the time it takes for half of the unstable nuclei to decay. So in other words, if I start with 100 grams, that's my initial value, that means after 0 minutes have passed, that means at the beginning of the problem, I have 100 grams of radioactive substance. After 10 minutes, that is after one half-life has passed, okay, I have 50 grams remaining. My starting amount has decreased by half in 10 minutes. Now, because of the way radioactive decay works, there's no way for me to know which specific atoms decayed or when each specific atom decayed, but half-life is kind of a probability type of thing. I don't know which ones did it, and I don't know when they decayed, but I know that on average, after 10 minutes, about half of them have decayed, on average. Okay, now, after 20 minutes have passed, that means after 2 half-lives have passed, between 10 minutes and 20 minutes, that's another 10-minute period. That's another half-life. Okay, now I have 25 grams remaining of this unknown radioactive substance. Notice that the rate of decay, on average, has changed. Here, I lost 50 grams over 10 minutes. Here, I lost 25 grams over 10 minutes. Okay, now I don't want you to think, oh, 50 grams over 10 minutes, that's 5 grams per minute. No, that's not, because it's not a constant rate of decay. Remember, it's exponential decay. And so actually the rate of decay changes over time. It's just that on average, during the first 10 minutes, I lost 50 grams over 10 minutes. Okay, so notice that as time passes, my average rate of decay is actually decreasing. Okay, because from 100 to 50 is 50 grams over 10 minutes. From 50 to 25 is 25 grams over 10 minutes, and so on and so forth. And so as time passes, my rate of decay decreases. We talked about that before, it decreases exponentially. So after each half-life, the amount of unstable atoms you have remaining has decreased by half. Not only has the amount of unstable atoms decreased by half, but also the rate has also decreased by a half. Okay, one of the interesting properties of exponential decay that you might learn about if you ever take calculus is that the rate of an exponential decay also has the same half-life as the amount. Okay, so after 10 minutes, not only has the number of grams of radioactive substance gone from 100 to 50, but the rate of decay has also decreased by half over that same half-life. Okay, so normally I would show you some simulations at this point, but the simulations I have are not working correctly, so I'm just going to do some more examples with Half-Life. Okay, pause it here if you need to write any of this down. I'm going to erase this. Okay, so this is just a picture showing a basic example of how this works. Let's say I start with 10 grams of cobalt-60. That means I have 100% remaining at the beginning after no time has passed, after 0 half-lives. And let's say the half-life of cobalt-60 is 5.27 years. That means on average, every 5.27 years, the amount remaining decreases by half. So after one half-life, that is after 5.27 years, I have on average 50% remaining. So if I started with 10 grams, I now have 5 grams of cobalt-60 remaining. Now you could ask, well, what happens to the other 5 grams? Well, it underwent radioactive decay and it turned into some other element plus radiation particles. Right? We could write the decay equation if we knew what the product was. And so it's not that that mass is gone per se, it's just it's undergone transmutation. There's been another element produced plus different types of radiation particles. Okay, so we've gone from 10 grams of cobalt-60 that we started with to 5 grams to 2.5 grams after 2 half-lives. And so you can see every half-life that passes, we go down by half of the previous amount. So let's do some very basic examples. Example 1. Barium-122 has a half-life of 2 minutes. A fresh sample weighing 80 grams was obtained. If it takes 10 minutes to set up an experiment using barium-122, how much barium-122 will be left when the experiment begins? Okay, so pause it here and see if you can answer this question. Okay, so I like to approach this type of half-life question through a chart. I'm given the half-life is 2 minutes. Okay, so T1 half is 2 minutes. Now, that means that at the beginning of the problem, if I have 80 grams, let's say, this is the mass of barium, is 80 grams when the time t equals 0 minutes. Okay, so I start with 80 grams. Now, after one half-life, that is, after 2 minutes have passed, right, from 0 minutes to 2 minutes is one half-life, I go down by half the previous amount. And I continue to do that every 2 minutes, like so. And I keep on going until I get to 10 minutes. Okay, so after 6 minutes, that's 10 grams. After 8 minutes, that's 5 grams. After 10 minutes, that is 5 half-lives. I'm at 2.5 grams. Now, the other way you could approach that is to say, okay, so the half-life is 2 minutes. 10 minutes is 5 half-lives. So that means I basically have to decrease by 1/2 5 times. And so you could also think of it like this. I start with 80. I want to decrease by 1/2. How many times? 5 times. And so if you're more mathy, you might want to think of it like this. If you're not so mathy, you might want to just make out a chart like this showing how it decreases by half every 2 minutes. It doesn't really matter how you do it. Okay, so the reason it's 1/2 raised to the 5 power is because I'm basically going to multiply by 1/2 for every half-life that passes. So 5 half-lives, meaning I have to multiply by 1/2 5 times. Either way, you get the same thing, right? Because 1/2 raised to the 5 power would be 1 over 64. Actually, sorry, not 64/32. And 80 over 32 is, guess what? 2.5. Okay, so either way you'd get the same thing. So let's just do a few more basic examples with Half-Life. Okay, I'm going to erase this here. Example 2 says if 10 milligrams of iodine-131 is given to a patient, how much is left after 24 days? The half-life of iodine-131 is 8 days. Okay, so again, simple problem. This is how much I start with. The half-life is 8 days, so T1 half is 8 days. And I want to know how much is left after 24 days. Okay, now 8 goes into 24 3 times, so this is after 3 half-lives have passed. Okay, so I can make out my chart. And I will say, by the way, one of the most common ways that people will mess up this chart is that they will not start at 0. Okay, some people might start this chart at 8 days. It should start at 0 days. After 0 days have passed, that means after no time has passed, you have 10 milligrams. You don't need to convert this, by the way. Your answer can also be in milligrams. After 8 days, that means after 1 half-life has passed, this is decreased by half of the original amount to 5 milligrams. After another 8 days, that means when you're at 16 days total, you decrease by half again to 2.5 milligrams. And then after one more half-life, half of 2.5 is 1.25. Okay, so the answer to the question is 1.25 milligrams of iodine-131 is remaining. Okay, so again, a very basic problem involving half-life. Now, keep in mind, a lot of radioisotopes have medical applications, which we're not going to talk about, but this is one of those types of situations where if you were a doctor giving iodine to a patient, for whatever reason, it would be useful to know that, hey, the vast majority of it's going to be gone in a month, right? And then you can tell them that, and they'll be happy to know that. Okay, so pause there if you need to write that down. We'll just do one more basic example. Okay, example 3 says the graph to the right shows how the amount of uranium-238 in a sample varies over time. Use the graph to estimate the half-life of uranium-238. Okay, so if we look at the y-axis here, this is showing the amount of uranium-238 remaining as a percent. Okay, now these graphs on the y-axis, either you typically see percentages, or you see masses, or sometimes you even see activity, because remember, the rate of decay has the same half-life as the amount itself. Okay, so by definition, the half-life is the time it takes, right, for the amount to decrease by half. So the time it takes to go from 100% to 50% right here, we can see right off the bat that that's going to be T1 half equals 4,500. But if you look at the units down here, this is time in millions of years. So 4,500 million years. Okay, which, if you prefer the half-life of uranium-238, if you wanted to write that in a different way, you could also say that's 4.5 billion years. Now, the reason I bring that up is because the age of the Earth is, in the 4 to 5 billion year range. And one way we know that we've talked about that before, is because uranium-238 undergoes a series of radioactive decays and eventually turns into lead, which is stable. And by taking rocks that are very old that we find on the Earth and measuring the ratio of lead to uranium-238 in them, we can easily figure out that about half of the uranium-238 has decayed in the oldest rocks. Now, because the half-life of uranium-238 is about 4.5 billion years, that gives us an idea that, hey, the Earth has to at least be as old as the oldest rocks. That's just logical. And so that gives us a way to predict the age of the Earth. Okay, now I'm going to erase this. Now, just to give you some examples of different types of radioactive materials and their half-lives. Some half-lives are very, very long. Rubidium-87, for example, has a half-life of 4.7. What is that? Times 10 to the 10 years. That would be 4.7. That would be 47 billion years. 47 billion years is really, really old. That's older than the age of the universe. For all intents and purposes, that might as well not even be radioactive, if the half-life is way older than the age of the universe. Uranium, you can see here, 4.5 billion years is pretty long. And then some things have shorter half-lives. Carbon-14, you can see, has a half-life of about 5,700 years. Now, what that means is if we want to use carbon dating to find out how old that is, we can only use carbon dating on something that was alive a couple thousand years ago. Because once we get past, say, 10,000 or 20,000 years, we've gone through several half-lives at that point, and at some point we lose the ability to precisely measure the amount of carbon-14 in a sample. And so carbon dating has limitations only to tens of thousands of years before we go through so many half-lives that the amount of carbon-14 is basically too small to measure. Cobalt-60 has a half-life of 5.3 years. Iodine-123 has a half-life of a couple hours. And these are just some typical half-lives, just so you can see the different range of half-lives. And there's no way to predict the half-life of a material just based off of where it is on the periodic table. That's always something you would be given in a question. I do want to point something out to you before we end this video, that notice if something has a longer half-life, that basically means it takes longer to decay. And if it takes longer to decay, that means the rate of decay is actually slower. Okay, that means the activity is less. So what I'm saying is that something that has a very short half-life, like oxygen-19, that has a short half-life because its rate of decay is very fast. Okay, so in other words, the higher the half-life, the shorter the activity, and vice versa. Okay, so on this chart, polonium-213 has a very short half-life. That means it would have a very high activity because it's going to decay very quickly. Whereas uranium-238 has a half-life of billions of years. That means it decays very slowly. Which, if you're thinking of, what type of radiation or what type of radioactive materials are dangerous, something that has a longer half-life is inherently less dangerous, just because that means it's not decaying as quickly as something else that has a shorter half-life. Okay, so just something interesting to point out. Okay, so I'm just going to maybe link these videos so that you can watch them about radioactive decay, and then in the next video we will move on back to models of the atom. Okay, as always, please let me know if you have any questions. I'll see you in the next video.